I will be presenting my recent work in silicon-Morse quantum computing. And this is a proof of principle experiment on the operation of a charge sensor that is capable of sensing at high temperature. So by high temperature, we refer that to above 1 Kelvin instead of millikelvin, which would usually require dilution fridge. This is very important to the qubit readout at that elevated temperature. And we know in a moment, this is important to developing a scalable quantum computer. So as a start, I will give a sense of the motivation behind this project, how it relates to the latest silicon-Morse quantum technologies. We know that a fully fledged quantum computer will require millions of physical qubits for fault-tolerant operation. Let's say if you want to achieve this using surface code error correction scheme, we will need a number of physical qubits to implement a logical qubit. And the fidelity of those physical qubits have to be above 99%, or an error rate of less than 1%. Operating every physical qubit comes with a cost because they have to operate at cryogenic temperature. So this study from Welthor's group estimates that with a single qubit consuming around 15 watts of cooling power, we would need about 500 microwatts if we want to operate 10,000 qubits. This is already far above the limit of any dilution fridge if we are operating at millikelvin. But if we operate at 1.5 Kelvin, for example, then we will have more than enough cooling power. Operating a silicon-Morse spin qubit at more than 1 Kelvin has actually proved to be feasible. Last year, our group published a paper on the high temperature operation of the single electron spin qubit in a silicon quantum dot. The important message from this paper is that it is possible to operate a spin qubit at 1.5 Kelvin with a single qubit fidelity of at least 98.6%, which is not too bad. This also makes sense because we operate the qubit in isolated quantum dots. So the spin initialization, control, and readout are all independent of the reservoir. Even though the thermal broadening in the reservoir is larger than the Zeeman splitting, it will have very little impact on the operation. We also saw that the shortest time scale for qubit operation, the T2 star here, it does not decrease that much as we move towards 1 Kelvin or above. And these are all promising signs that we can indeed operate qubit at that temperature. And there was also a similar work from the Welthor's group. They observed a similar single qubit gate fidelity, and they also tried for the first time 2 qubit gates at high temperature, and ended up with lower fidelity of about 86%. One thing we noticed from those experiments was that the measurement fidelity is strongly limited by the single electron transistor we have been using for charge readout. And that made us think about new methods for high temperature qubit readout and charge sensing. One idea we had was to use a double island SET instead of the single island SET, which has been the standard so far. On the left, we have the schematic for a single island SET and a double island SET. A single island SET always has electron transport between the island and the thermally broadened reservoir, whereas the double island SET has one tunneling that happens between the discrete energy state in the island that makes it much less sensitive to any influence from the temperature or thermal excitation in the reservoir. From now, for convenience, I will refer to the single island SET as a side set and the double identity as a die set. On the right, the device we have fabricated looks like this. We basically have two kinds of gates. We have this blue gate, not this one. So we have these top gates that we use for accumulating electrons underneath the silicon interface to form the reservoirs or the islands. And we also have these little green gates that we set slightly less positive voltage to form the tunnel barrier between the islands and the reservoirs. On the top, we have this reconfigurable side set or die set depending on the voltage setting on the SRB. So if we set the SRB to a semi-transparent point, just like any other barrier gates, then we have a full die set. But if we fully turn on the SRB and extend the reservoir to the right island's location, then effectively we have a side set. And below is a structure to define a single quantum dot that we can controllably load single electrons. We know that in qubit readout, we perform spin to charge conversion, and the resulting charge movement is detected by the SET. Here, we're just using the electron movement in the single quantum dot to assess the effectiveness of charge sensing with different SET configurations on top. So a few important things from our work. We basically demonstrate a few things. The first is we show that the die set can produce notably sharper Coulomb peaks than the side set at high temperatures. And this is what we expected from the theory. And for the first time, we also showed charge sensing with a die set in both the low frequency lock-in and single shot measurement scheme. In charge sensing, we observed that the die set has notably higher charge sensing signal to noise at high temperature because of the sharper Coulomb peaks. And as a result, we also have a higher charge readout fidelity. We have up to 99.9% at 1.7 Kelvin with the die set. And along the way, we also established a theoretical model for the electron transport through a die set. So this is complementary to the single dot transport model that has been developed in many of the papers. So for the theory, we have details in the supplementary material of the paper. Now, for us to have an initial understanding of the operation of the device operation, we measure the transport characteristic of the SET. All the data coming from the side set will be plotted in red, and the data from the die set will be plotted in blue. So the single electron tunneling event in the side set is basically shown as Coulomb oscillations or Coulomb diamonds, depending on the sweeping of the gates. And the transport through the die set, we can see it as the triple point or bias triangles, depending on the source strength bias condition. So from these patterns, we can extract a range of important device parameters that we can use for data analysis or any other characterization. And more importantly, through this analysis, we also obtain important information on tuning of the SETs. This is crucial because we want to optimize both SETs for our later charge sensing experiments. And the details of how to tune the die set in particular is also given in the supplementary material. And I can talk about that at the end. After tuning up the SET, if you now measure the 1D strips of the Coulomb peaks at different device temperatures, we can now see how the peaks evolve as the temperature goes up. How do we take these peaks? For the size set, we simply vary the top gate voltage to shift the energy levels in the single island, with everything else kept the same. And for the die set, we take a line cut along the detuning direction in the 2D bias triangle. We can see that size set has pretty standard Gaussian peaks, as we would expect. And they broaden drastically as the temperature increases. Now, the interesting thing for the die set is we see asymmetric peaks that is steeper on the left side and has something more like a shoulder on the right side. So the left side is because of resonant tunneling across the two islands in the die set, and the right side is due to the relaxation. So the resonant tunneling involves only the discrete energy levels, and there is no relaxation of any sort. So we can see it hardly broadens with the increasing temperature. But on the other hand, the inter-island relaxation, it becomes more prominent as we go for higher temperatures. So we can see that it broadens as much as the size set. So in order to quantify these results, we numerically extract the slope of the Coulomb peaks and plot it as a function of temperature. So we define the slope as the amplitude divided by the full wave half maximum. So this is just a very simple triangular approximation to the Gaussian peaks for both SETs. We can see that at 1.7 Kelvin, which is the base temperature of our system, the die set already offers about twice the slope as the size set, and we're having more improvement as the temperature increases towards 8 Kelvin, where we have about 5 times improvement. But we also notice that after 8 Kelvin, this advantage begins to diminish. And we also see a deviation between the measurement data and the simulation. And this is because the thermal broadening approaches and overcomes the Coulomb blockade window. And we're no longer having well-defined single electron transport in the die set. Now we begin to get into the highlight of this work, which is the charge sensing. So we tune both SETs to the most sensitive points, and we begin with using the AC lock-in technique to measure the charge transitions. Essentially, we apply an excitation to the dot top gate and track changes in the SET current as a result of this excitation. If we measure that as a function of the gate voltages, then we obtain single dot charge stability maps, as we can see on the left panel. The vertical lines that you see here represent the charge transition in the single dot. And these charge sensing maps, they take quite long, so we measure it only at the important temperatures. 1.7 K again is the base temperature, and 4.2 K is the liquid helium temperature, and 8 K is where the die set begins to get overwhelmed by the thermal excitation, as we have just seen. So we have the 2D map versus the top gate and the barrier gauge of the dot on the top, and at the bottom we also plot a 1D line cut at certain barrier gate voltages. So this is just to visualize the strength of the transition signals. In order to quantify the dieset improvement, we extract the signal strength, the output noise level, and the signal to noise from these peaks, from these transition peaks. So we can see that at 1.7 Kelvin, the dieset signal is about twice the size of signal. And at 8 Kelvin, we have several times larger signal in the dieset, which is consistent to the Coulomb peak slope. And we know that we also have a similar temperature dependence in the output noise, which makes sense because while the SETs are more sensitive to signal, it's also more sensitive to the noise. We found that dieset signal to noise is limited to about 5 dB higher than the dieset, since the low frequency noise dominates our lock-in measurement scheme. We also noticed that the lock-in signal is smaller than the actual charge transition signal because of the internal configuration of our lock-in amplifier. So this leads us to the single shot measurement. And in fact, this is a closer approximation to qubit readout, since we mostly detect spin to charge conversion in single shots in real time. And here we tune the quantum dot to one of the charge transition points, and we observed consistent telegraph signals in real time. We then map those time traces into the histograms with the 2 peaks representing the 2 levels. And from these histograms, we can do 2 things. We can again calculate the signal to noise, and we can also extract the charge readout error, from which we can get the fidelity. So the signal level of the single shot sensing is given by the separation of the 2 peaks, and the error and the noise is given by averaging the standard deviation of the 2 peaks. And if we want to calculate the error, we get it from the overlap between the 2 Gaussian peaks. So we took the measurement at the full bandwidth of 200 kilohertz, and we applied low-pass filtering of different cutoff frequencies to represent different measurement bandwidth. We then plot the signal to noise and readout error as a function of the measurement bandwidth. And also in the inset, we plot the temperature dependence again at the bandwidth of 7 kilohertz. Okay, so we first look at the signal to noise ratio. So we can see that the signal to noise reduces as the bandwidth increases, as we would expect. We also see a similar temperature dependence to that we got in the lock-in sensing, but just that this time we have more improvement. So we have just short of 10 dB improvement at 1.7 Kelvin, and we have as much as 15 dB improvement at 8 Kelvin for the dieset. So in general, the dieset has a better performance, has a larger improvement from dieset in this sensing mode compared to the lock-in sensing, because the high frequency noise from measurement setup dominates. So the measurement is pretty fast. We don't integrate over a long time. So as a result, we are not picking up a lot of the low frequency noise probably happening out here. We do have high frequency noise at probably 100 kilohertz or so. But over the majority of the frequency spectrum, yeah, we're seeing we are not picking up a lot of the noise, and for the dieset we have a much better signal to noise ratio. Finally, we would like to know what these results imply for high temperature qubit operation. So for this, we define the charge readout fidelity. It defines a threshold of 99.9%, and we look for the bandwidth corresponding to this error rate at each temperature for the SETs. We chose this threshold value because it crosses the curve for both SETs. So this is somewhat arbitrary, just to get a side-to-side comparison between the two SET configurations. If you do use a standard threshold value, for example, the 99% for the surface code error correction, then we find that the die set can actually operate above 4.2 Kelvin. So this means that possibly readout is no longer a limiting factor on qubit measurement fidelity. On the right side is a little figure that shows the effect of the temperature on the operation of a future quantum processor. So the blue lines is the maximum bandwidth for the die set to have a charge readout fidelity of 99.9%. And the red line is the bandwidth for the psi set. We also have some requirement due to the limited coherence and lifetime of the qubit. So the first gray line represents the slowest speed we can measure within 1% of the phase flip error from T2 Huang. And the second gray line represents 1% bit flip error from T1 relaxation. So of course, we have ignored here the spin to charge conversion fidelity. So when we read out the spin, you can also relax before it gets picked up by the charge sensor. But we couldn't really measure that here, so we're just assuming things are all happening during the charge detection. So basically, the bottom line message is we stay above the gray lines to read out within the decoherence and relaxation limit, and we stay below the color lines to ensure a high enough readout fidelity. And based on this, we find that to measure the die set, to measure the size set within T2 Huang, we have to operate at below 240 millikelvin. And to measure with the die set, we can do it at 1 Kelvin in a somewhat fault tolerant way. So in summary, we proposed a double island SET design utilizing the alignment of discrete energy levels to have sharper Coulomb peaks. And as a result, we have up to several times sharper Coulomb peaks, as we've seen in the transport measurement, and we have 5 to 15 dB improvement in the charge sensing, depending on which mode we operate in. We also have much higher charge readout fidelity with die set. We're hitting 99.9% in T2 Huang at 1 Kelvin. So this is important because at this point, we can already get rid of the dilution unit and operate in the pump helium force system. And we can also operate with the fidelity of 99% at 4.2 Kelvin in the liquid helium force system. If we were to implement this highly sensitive die set. On the contrary, the size set will always require below 1 Kelvin and has to rely on dilution system. So one thing though for the die set, we'll be having more complicated footprint, some additional gates, and we also have some complications in tuning. But it's still very promising and worth our approach to achieve high temperature charge readout in the future quantum computing. And yeah, that's all for my talk. Thanks for listening, everyone.